Hello dear students, we will study some of the concepts regarding the chapter moving charges and magnetism. This is the chapter number 4 of your NCERT textbook. We have studied electric charges and fields, we have studied electric potential, and we have studied current electricity. Okay, so we have studied a charge produces electric field, correct? A charge produces electric field, a mass produces gravitational field. To produce magnetic field, the essential thing is moving charge. So that is why name of the chapter is moving charges and magnetism. What does it mean? Only moving charges produce magnetism. If a charge is at rest, it will only produce electric field. That we have studied already. Okay, but if a charge is moving, it will produce magnetic field. Probably in your high school you might have studied a current carrying conductor, it produces magnetic field, correct? And there will be magnetic field lines around a current carrying conductor. Means current carrying conductor is at rest, but inside the current carrying conductor, electrons are moving. Since the charges are moving, they produce magnetic field. So this is a very important thing. Understand the chapter head, moving charges produce magnetism. Okay. Now, how do we define magnetic force? If I have to define magnetic force, what is gravitational force? Force experienced by a mass when placed in gravitational field is called gravitational force, correct? Okay, well, then what is magnetic force? Magnetic force is the force experienced by a charge. Okay, it is the force experienced by a charge or a current carrying conductor when it is placed in a magnetic field. So I'll just write magnetic force. What is it? Is the force experienced by, it is the force experienced by a charge or a current carrying conductor when placed in a magnetic field. Okay, when placed in a magnetic field. Okay, then how does the equation for magnetic force look like? Magnetic force on a charged particle. Okay, magnetic force on a charged particle. Say there is a magnetic field in this direction. Say this is the magnetic field. Okay, this is the magnetic field. Say the charged particle is moving in this direction with velocity v. Okay, charged particle moves in this direction with velocity v. Okay, now force on the charged particle. Okay, force on the charged particle is directly proportional to magnitude of charge, 1 point. Okay, if the charge is more, then the magnetic force experienced by the charge is also more. Like in the case of gravity, if the mass is more, gravitational force is more, correct? If the mass is less, gravitational force is less. Okay, that's 1 point. Then force is directly proportional to strength of the magnetic field. If the strength of the magnetic field is more, then the magnetic force is more. Like in the case of electric field also, F is equal to Q into E. If the strength of the electric field is more, then the electric force is also more, correct? F is equal to Q into E. Then one interesting point here is, it is also directly proportional to, see, this angle is theta. What is this theta? Theta is the angle between magnetic field and the velocity, correct? Vertical component of velocity, what is this? This will be V sin theta, correct? Horizontal component of this velocity will be V cos theta. This is V cos theta. This will be V sin theta. Magnetic force is directly proportional to vertical component of velocity, or a component of velocity perpendicular to the direction of field. Perpendicular to the direction of magnetic field, there has to be some velocity, otherwise magnetic force will be 0. See, force on a charged particle is given by F is equal to QVB sin theta. F is equal to QVB sin theta. What is theta here? Theta is the angle between V and B. Okay, velocity and magnetic field. Now we know this. A cross B is equal to AB sin theta, correct? A cross B is equal to AB sin theta. Then what is VB sin theta? VB sin theta will be V cross B. In vector form we can write F is equal to Q into V cross B. F is equal to Q into V cross B. Magnetic force will be 0 if the charge is 0, or the magnetic field is 0, or the vertical component of velocity is 0. Okay, so this is the expression for magnetic force on a charged particle. Now, one simple problem. Okay, an alpha particle, an alpha particle, and a proton are projected with same velocity, enter a uniform magnetic field. Okay, find the ratio of forces. Okay, so force on a charged particle. What is the formula we should use here? F is equal to q v b sine theta. Okay, so we should find the ratio. What is an alpha particle? Alpha particle means helium nucleus, correct na? So alpha particle will have two protons and two neutrons, correct na? Neutrons are neutral, so they don't experience magnetic force. Proton means, okay, one proton is there. Okay, so F is equal to what we have to find out? Find the ratio of forces. Force on alpha particle divided by force on proton. Force on alpha particle divided by force on proton is equal to charge on alpha particle, velocity of alpha particle, magnetic field into sine theta, correct now, divided by, so charge of proton into velocity of proton, magnetic field on proton into sine theta. Okay, what is charge of alpha particle? Charge of particle, alpha particle has two protons, na, one proton. Charge of one proton is E. Charge of two protons is 2E. Okay, divided by what is charge of proton? E. Okay, then they move, they are projected with same velocity. Same velocity means the velocity of alpha particle is equal to velocity of proton. Okay, then enter a uniform magnetic field. So magnetic field also should be same, and they are not speaking about the angle. So sine theta also should be same in both the cases. So therefore all these terms gets cancelled. E and E gets cancelled. So what is the ratio? The ratio of the forces is equal to 2:1. Okay, it's a simple problem. Now what we will do? We will study motion of a charged particle in a uniform magnetic field. So before that we need to know something called Fleming's left hand rule. Okay, it gives the direction of force on the charged particle. Okay, so what does it say? If you stretch the first three fingers of a left hand in mutually perpendicular directions, okay, if the forefinger points the direction of magnetic field, okay, you should hold your finger such that forefinger points the direction of magnetic field, and if the central finger gives the direction of velocity, then the thumb gives the direction of force. Okay, you will understand once we use it. Okay, just I'll read out the statement once. If the first three fingers of the left hand are stretched in three mutually perpendicular directions such that the forefinger is along the direction of magnetic field, central finger is along the direction of velocity of the particle, then the thumb gives the direction of magnetic force. I'll just explain what it is. Okay, say there is a uniform magnetic field. Say this is a uniform magnetic field. Okay, say the charged particle is shot upwards. Okay, so this is the direction of velocity of the charged particle. According to Fleming's left hand rule, what you should do? You should place your forefinger such that it points the direction of magnetic field. Magnetic field is in this direction, correct now? And if the central finger gives the direction of velocity, okay, then the thumb gives the direction of force. So what is the direction of force? Direction of force is into the plane of the board. Okay, or if say this is the direction of magnetic field. Okay, this is the direction of magnetic field, and say the charged particle is shot down. Okay, velocity of the charged particle is downwards. Then forefinger should show the direction of magnetic field. Central finger gives the direction of velocity. Then thumb will give you the direction of force. Direction of force is towards you. Okay. Now here what happens? In see, there are three directions, no, X, Y, and Z. So it is very difficult to analyze or represent these diagrams in two-dimensional board. So that is why we do some adjustment. What is that? If the magnetic field is going into the plane of the board, then we write it like this. Okay, if the magnetic field is coming out of the plane of the board, then we represent it like this. That means say I draw a diagram something like this. Okay, then I write B somewhere here. What does it mean? It means there is a uniform magnetic field, means spacing between them is same. Okay, uniform magnetic field, and that uniform magnetic field is going into the plane of the board. If the uniform magnetic field is going into the plane of the board, then you put into symbol. Okay, say in this, say here in this region, I have written like this. Okay, what does it mean? And I write B. What does it mean? Here in this region, magnetic field lines are coming out of the plane of the board. Okay, if I represent like this, okay, then what is the advantage? Let me see. Say I consider a uniform magnetic field. Okay, so if I write like this, what is the meaning? Here there is uniform magnetic field, and the magnetic field lines are going into the plane of the board. Now, say the charged particle is fired in this direction. Velocity of the charged particle is this. Now you apply Fleming's left hand rule. Your forefinger should point in the direction of magnetic field. Okay, where is magnetic field? Magnetic field is into, correct now? Magnetic field is into the plane of the board. Yeah, into, correct now? Into. Central finger should give you the direction of velocity. Okay, this gives the direction of velocity. Then the thumb will give the direction of force on the charged particle. Now, to represent these three directions like this, it is easy. Okay, that is why currents or magnetic fields can be represented like this using into symbol or by putting a dot. Okay, so that for us it becomes easy to analyze the situation. Okay, now what we will do, we will come into the main topic. Okay, motion of a charged particle in a uniform magnetic field. So here basically we are analyzing this equation. F is equal to QVB sin theta. Okay, so what if theta is equal to 0 degree? What if theta equal to 180 degree? What if theta is equal to 90 degree? All those things we are going to discuss. Say first subdivision. If theta is 0, if theta is equal to 0 degree, or theta is equal to 180 degree, then what happens? So there is a magnetic field in this direction. There is a uniform magnetic field in this direction. A charged particle plus q is shot in the direction of magnetic field. So what is the angle between magnetic field and velocity? Angle between magnetic field and velocity is 0. So then what is sine 0? Sine 0 is 0. Force is 0. Magnetic force is 0. Even though the charged particle is moving in the magnetic field, if the angle between magnetic field and velocity is 0, magnetic force is 0. Means charged particle moves as if there is no magnetic force, as if there is no magnetic field. Okay, this is strange. Correct now? If you place a mass in a gravitational field, whatever may be the direction of velocity of the mass, it will experience gravitational force. Even it is true in the case of electric field, but magnetic field is little strange. Okay. Now here there is no magnetic field. See, I have explained you before. There should be component of velocity perpendicular to the direction of magnetic field. Here all the velocity is in the direction of magnetic field, so there is no magnetic force. If theta is equal to 180 degree, okay, if theta is equal to 180 degree, say this is the direction of magnetic field towards your right. Say the charged particle is moving opposite to the direction of magnetic field. Now also, angle between velocity and magnetic field is 180 degree. Sine 180 is 0. Force is 0. What does it mean? If the charged particle is moving in the direction of magnetic field, or if it is moving opposite to the direction of magnetic field, okay, it moves in a straight line. Okay, it moves with a constant velocity. Why it moves with a constant velocity? Force is 0. Correct? If force is 0, F is equal to m into 0, m into a. If force is 0, acceleration is also 0. Acceleration is 0 means there is no change in velocity. The charged particle continues to move with the same velocity. Okay. Now, the second case. This is very important one. Okay, second case. If theta is equal to 90 degree, the angle between velocity and magnetic field is 90 degree. Okay, now we will analyze. Okay, let me consider one uniform magnetic field. I have considered one uniform magnetic field. This is very important. Listen. I have considered one uniform magnetic field. Okay. Say there is a charged particle inside plus q, and it is moving with velocity v perpendicular to the direction of magnetic field. Perpendicular means magnetic field is into the plane of the board, na? So velocity is in this direction, perpendicular. Now what happens? See, forefinger should give you the direction of magnetic field into, okay. Then the central finger should give you the direction of velocity. Correct, na? Correct. Hope you can understand. Correct, na? Magnetic field is into, velocity is in this direction. Then thumb gives the direction of force. So it experiences a force in this direction. It experiences a force in this direction. So slowly, instead of going in this direction, slowly the charged particle starts moving like this. Okay. Now, say when the charged particle comes here. Now, what is the direction of instantaneous velocity of the charged particle at this point? Along the tangent. Correct now. Here you analyze. Magnetic field is into the plane of the board. Okay, velocity is going up. Okay, force is in this direction. Okay, force is in this direction. So because of that, instead of moving in this direction, the charged particle again takes a turn and slowly comes like this. When the charged particle comes here, direction of velocity of charged particle is in this direction. Now again you here you apply Fleming's left hand rule. Forefinger is into the plane of the board. Okay. Central finger gives the direction of velocity. So force is downwards. Means there is a force. There is always a force which is acting towards the center. So this magnetic force will be the centripetal force. Correct? Now, towards the center. So the charged particle comes here. Again here, the direction of velocity of the charged particle is this. Magnetic field is inside. So the velocity of the charged particle is downwards. Okay, force is towards the center. So the charged particle moves in a circular path. When a charged particle is shot perpendicular to the direction of magnetic field, it will move in a circular path. Now, here it is like charged particle is trapped. It is trapped. Okay. So it will continuously move in a circular path with a constant speed. Why it will move in a constant speed, we will see. Okay. At any point, say I consider one point here. I consider this point. Okay. This one. What is the direction of instantaneous displacement? Direction of displacement at this point is this. Correct now. What is the direction of force? Force is in this direction. Displacement is in this direction. Correct now. So angle between force and displacement is 90 degree. Then what is work done? Work done is equal to fx cos theta. Correct now. Work done is equal to fx cos theta. Theta is equal to 90 degree. Means cos 90 is 0. So work done is 0. And the charged particle is moving in a circular path. Work done is 0. If work done is 0, we know that from first PUC we have studied change in kinetic energy equal to work done. It is called, what is that? Work energy theorem. Work energy theorem says that change in kinetic energy is equal to work done. What is change in kinetic energy? Final kinetic energy minus initial kinetic energy is work done. Work done is 0 here in this case. So therefore, final kinetic energy is equal to initial kinetic energy. Final kinetic energy is equal to initial kinetic energy. Means final speed is equal to initial speed. Means when the charged particle is moving perpendicular to the direction of magnetic field, speed will not change. Force is acting on the charged particle, but speed will not change. It is very strange. If a ball is dropped in a gravitational field, okay, what happens? Speed of the ball increases. Okay, when the charged particle is kept in an electric field, its speed will either increase or decrease. Correct now. But in the case of magnetic field, if the velocity of the charged particle is perpendicular to the direction of magnetic field, then the speed will not change. Okay, why speed will not change? We have proved it. Correct now. Since the angle between instantaneous displacement and force is 90 degree, so therefore work done is 0. If work done is 0, change in kinetic energy is 0. Final kinetic energy minus initial kinetic energy is equal to 0. So final kinetic energy should be equal to initial kinetic energy. That means final speed should be equal to initial speed. Hope you understood this. Okay. Now what we'll do? In the same case, what is that? Charged particle is shot perpendicular to the direction of magnetic field. In the same case, we will derive expression for radius of the charged particle and time period and frequency. Okay. Say what we have taken. We have taken a charged particle plus q, and it is short such that angle between magnetic field and velocity is 90 degree. Okay, now we know that, just now we studied that this charged particle will move in a circular path. Okay, now at any moment here, the magnetic force is acting in this direction, correct? Now magnetic force is acting in this direction. So magnetic force, this is very important, magnetic force is responsible for centripetal force. Magnetic force is responsible for centripetal force. Okay, magnetic force, what is magnetic force? QVB sine theta, correct? Now what is theta here? Theta means what? Angle between velocity and magnetic field. So theta is equal to 90. Sine 90 is 1. That, okay. So sine theta I don't have to write. Sine theta, okay, is 1, is equal to mv square by r. Mv square by r. What happens? One v and one v gets cancelled. So I can write the equation for r. R comes here. R will be equal to mv by qb. Okay, r will be equal to mv by qb. If the mass of the charged particle is more, then the radius is more. If the velocity of the charged particle is more, then the radius is more. If the charge of the charged particle is more, then the radius is less. Or if the magnetic field is more, then the radius is less. So this is the expression for radius. Okay. Once I get the equation for radius, I'll try to derive an expression for time period of revolution of charged particle. What is time period? Time means basically, what is the formula? Time means distance by speed, correct now? Time means distance by speed. Okay. Time period means what? Time required for one revolution. In one revolution, what is the distance traveled by the charged particle? In one revolution, distance traveled by the charged particle is equal to circumference. Is equal to circumference divided by speed. What is the circumference of the circle? Okay, sir, what is the circumference of circle? 2 pi r divided by speed. Now I have derived equation for r. Na? What is r? R is equal to mv by qb. Let me substitute. Okay, let me substitute. What happens? T will be equal to 2 pi by v into r. R means what? mv by qb. So v gets cancelled. Time period of revolution is given by 2 pi m by qb. What does it mean? Time period of revolution of a charged particle is independent of speed of the charged particle. Whatever may be the speed with which you fire the charged particle inside a magnetic field, time period is same. Why? If you increase the speed of the charged particle, okay, if you increase the speed of the charged particle, radius of the charged particle will increase. Radius of the charged particle will increase. Okay, means this is very important. Means if the charged particle is fired slowly, then it will move like this. Okay, if the charged particle is fired with very high speed, then it will move like this. Even though the speed is more, time required to complete one revolution is same. That you can see in the equation of time period. There is no trace of velocity. Okay, so hope you understood this. The second case, when the charged particle makes an angle, velocity of the charged particle makes an angle 90 degree, then what happens? It will move in a circular path. Speed of the charged particle will be same, and we have derived expression for radius of the charged particle and time period of the charged particle. If this is the time period, then what is the equation for frequency? Frequency is equal to qb divided by 2 pi m. qb divided by 2 pi m, because we know that frequency is equal to 1 by time period. Or if you shift this 2 pi here, what happens? 2 pi f is equal to qb divided by m, or 2 pi f. What is 2 pi f? Omega, correct now? Angular frequency omega is given by qb by m. Okay, time period is equal to 2 pi m by qb, frequency equal to qb by 2 pi m. Now the last case, the third case. If theta is not equal to 0 degree, theta is not equal to 90 degree, and if theta is not equal to 180 degree, if theta is not 0, if theta is not 180 degree, if theta is not 90 degree, then what happens? We will see. Say, I have considered some uniform magnetic field. Now the charged particle, say the charged particle plus q is fired such that its velocity is making an angle theta other than 0, 90 and 180. Now what happens? It's very important. Now what happens? I'll just you see. We have seen. If the charged particle is fired in the direction of magnetic field, then it will go straight. Correct? No? It will go straight because force experienced on that charged particle is zero. Okay, first case it is. First case. If the charged particle is fired such that its velocity is making an angle 90 degree with the magnetic field, then it will move in a circular path. Correct now? Means this perpendicular component of velocity is responsible for force. Because of perpendicular component of velocity, the charged particle will move in a circular path. Because of parallel component of velocity, the charged particle will move straight. Now here, this is very interesting. Now this velocity will have a parallel component of velocity. This will have a parallel component of velocity, and this will have a perpendicular component of velocity. Because of perpendicular component of velocity, the charged particle moves in a circle. Okay, because of parallel component of velocity, charged particle moves forward in the direction of magnetic field. So therefore, as a result of these two forces, the charged particle moves in a helical path. The charged particle moves in a helical path. Hope you can understand. Because this velocity has got two components. Due to parallel component, it will go straight in the direction of magnetic field. Due to perpendicular component, okay, perpendicular component means what? So the previous discussion. So here, if the velocity is perpendicular to the magnetic field, then it will move in a circular path. Since here in this case, there are both components. Parallel component, due to parallel component, charged particle moves in the direction of magnetic field. Due to perpendicular component, charged particle moves in the circular path. Since both of them are, okay, both of them are present, it should move in a circular path. Also, it should move forward. So therefore, what happens? So you will get a helix, correct? Na? You will get a helix. Okay. The charged particle move in a helical path. Okay. Now, this distance we call it as pitch of the helix. This distance we call it as pitch of the helix. So what is pitch? Pitch is the horizontal distance traveled by the charged particle in the direction of magnetic field during a time equal to time period. Because so here to here, one complete circle is over, na? Okay. So therefore, what is pitch? How to derive an equation for pitch? Pitch is equal to horizontal component of velocity, horizontal or parallel component of velocity into time taken. Time taken is one time period, correct? Na? So what is V parallel? V parallel is equal to V cos theta. V parallel is equal to V cos theta into what is the equation of time period? Time period is equal to 2 pi m by qb. So this is the equation for pitch of the helix. Okay. So hope you understood all the concept that I explained today. So basically what we did, we wrote an equation for magnetic force. Magnetic force is equal to QEV sine theta, or in vector form, magnetic force is given by Q into V cross B. Q into V cross B. Then we studied Fleming's left hand rule. According to Fleming's left hand rule, if you stretch first three fingers of your left hand, if the forefinger points in the direction of magnetic field, if the central finger points in the direction of velocity of the charged particle, then the thumb will give you the direction of force on the charged particle. So using that, we studied how the charged particle moves in a magnetic field. If the angle between velocity and magnetic field is 0 or 180 degree, the charged particle moves straight. Force on the charged particle is 0. Okay, if the velocity, if theta is equal to 90 degree, then the charged particle moves in a circular path. Correct now? Radius of that circular path is given by mv by qb. Time period of revolution is given by 2 pi m by qb, and frequency of revolution is given by qb divided by 2 pi m. Then what we studied, if theta is any other angle other than 0, 90 and 180 degree, okay, then what happens? Then the charged particle moves in a helical path. Okay, distance traveled by the charged particle in the direction of magnetic field in a time equal to one time period, we call it as pitch of the helix. So the pitch of the helix is given by horizontal component of velocity into time period 2 pi m by qb. So this is what we have studied in this session. Hope you understood all the points. Okay, you please make notes of this. You don't understand means you just listen to it one or two times more. Okay, then do a detailed clear notes. Thank you very much.